Can you connect these 9 dots with 4 consecutive lines without lifting your pen from the page? Take a look at this example, where we missed the dot in the middle. Feel free to pause the video and ponder on this puzzle, but be warned, you need to think outside the box to solve it, even if the borders of this box are invisible. Today's video is all about thinking outside the box. In the puzzle from the intro, this box is a limitation people tend to set themselves. A box with invisible borders, if you like. Before we unveil the solution to the 9 dots puzzle, let's explore 2 real-life scenarios where thinking outside the box transforms complex problems into simple solutions. The first story quite literally revolves around boxes. Imagine working in a toothpaste factory. At the final stage of the assembly line, the machine aims to package the freshly made toothpaste tubes into neat boxes. Usually, this process runs smoothly, resulting in perfectly packaged tubes ready for shipment. Occasionally, however, the packaging machine malfunctions, leaving us with empty boxes, an undesirable outcome. At the crucial point just before shipping, we face the challenge of identifying and eliminating these empty packages. How can we ensure that only the filled boxes make their way down the assembly line? This perplexing dilemma presented itself to the management team, demanding an innovative solution. As the urgent need for a solution arose, the executives swiftly mobilized a team of skilled contractors and experienced consultants. They came up with an addition to the assembly line, right before the boxes are dispensed into the shipping containers. First, they added a scale to the assembly line that could determine the weight of an object lying on the very same assembly line. To detect whether a box is above the scale or not, a sensor with a laser was added next to the assembly. Finally, to eject the boxes, a piston was installed in range of the boxes. Now, if a box potentially filled with a fresh tube of toothpaste passes the line, the laser detects the box and the custom-made control unit stops the line. The scale measures the weight of the box and, if it is considered to be too low and therefore empty, the piston is activated and pushes the box off the assembly line. If the box was not determined to be too light, the piston would not activate and the assembly line would continue transporting the boxes. This solution cost the factory around $50,000 and had a success rate of around 80%. The workers were only partly pleased with this solution. Often, the laser would get dirty, halting the assembly line until the dirt was removed, thereby delaying production and adding cost. Other times the piston would get stuck or break completely. Such problems accounted for the remaining 20% failure rate. The workers, however, know how to help themselves. They came up with a solution that was as simple as it was genius. They introduced a fan to the assembly line. The airflow generated by the fan was enough to push empty boxes off the line, but not enough to interfere with the passage of boxes containing a tube of toothpaste. This solution cost $20 and had a 100% success rate, as long as the fan was on at least. The empty boxes were not the only ones to be blown away by this brilliant solution. As you may remember, we kind of are a maths and science channel. So this second example is a fairly advanced maths problem, far outside everyday mathematics, and hence it requires quite some skill in order to solve it. But maybe we can find a second solution that requires almost no maths at all. Let's have a look at the problem. We want to solve the infinite sum x equals 1 plus 1/2 plus 1/4 plus 1/8 and so on. Note that we also use the notation with the sum symbol. If you are not familiar with this, don't worry, it is not needed for this video. We aim to solve this problem completely, which is why we avoid using the geometrical series, which would provide a general solution to such problems. The idea for our solution is quite standard. First, find the solution for the finite case and then take the limit as n goes to infinity. Let us call the finite sum a. We can write a equals 1 plus 1/2 plus and so on until 1 divided by 2 to the k, where k is some arbitrary natural number. Now that we are already on it, let's also calculate 1/2 a. Dividing all the terms from a by 2, we arrive at 1/2 a equals 1/2 plus 1/4 and so on until 1 divided by 2 to the k plus 1. Let me just quickly rewrite this and add some color coding. Note that nothing happened in this step, we just wrote it out more elegantly. If we now subtract the upper from the lower equation, all the green terms cancel out, resulting in a minus 1/2 a equals 1 plus 1 divided by 2 to the k plus 1. Since a minus 1/2 a equals 1/2 a, we can write it as such. Multiplying both sides by 2 yields our general solution for the finite case. A equals 2 plus 2 divided by 2 to the k plus 1. Let us remove the calculation steps and continue deriving the infinite sum. All that is left to do is to notice that x equals the limit as k approaches infinity of a, which is equal to the limit as k approaches infinity of 2 plus 2 divided by 2 to the k plus 1. Obviously, 2 to the k plus 1 becomes infinite as k approaches infinity. Since this term is in the denominator, the term 2 divided by 2 to the k plus 1 becomes 0. This results in x equals 2 plus 0 and therefore the final solution x equals 2. This is actually a very well known infinite sum and some of you may be aware of more elegant solutions to arrive at the final value of 2. But I think we can solve this problem with basically no maths at all. First, let's draw a 1 by 1 square in blue. The area of this square is 1 times 1 equals 1. If we halve this square along one of the edges, we get a rectangle with an area of 1/2 times 1 equals 1/2. Let's place this rectangle next to our original square. Now we halve the purple rectangle along the long edge, which again gives us a square, this time with area 1/2 times 1/2 equals 1/4. Now we just repeat the process. The next rectangle will have area 1/8 and so on. At this point, the regularity in this geometric arrangement of squares and rectangles becomes apparent. It's exactly the same series as before. 1 plus 1/2 plus 1/4 plus 1/8 and so on. From the arrangement we see that if we continue forever, a larger rectangle shape will be approximated closer and closer. This larger rectangle has edges with lengths 1 and 2. Now comes the only step that requires calculation. The infinite sum is equal to the total area of all these rectangles together, which is equal to 1 times 2 equals 2. This gives us the same solution as before, no limits and no algebra required at all. If you made it this far, you are probably wondering about the 9 dots problem from the intro. Let's have a look at the solution. As mentioned in the beginning, you need to leave the invisible box around the points, literally. So, if there is any lesson to be learned from this video, let it be this: step outside the invisible limitations you set yourself. By the way, it is also possible to solve this problem with only 3 lines. Okay, bye.